Coding Initiative. Adila and I are together with a colleague from the Butler Library running a workshop on digital archives. There are many different things, and people who went last year were quite happy with it. It's Keble College, so it's like being in a Harry Potter movie basically for a week. If you want to come to the meeting is, so the information meeting, it's just half an hour. It's the 21st of January at 2 o'clock, and this is at the History Department, so 1461 at 516. Another thing I wanted to just get your attention to was CEDAR, so the Center for Digital History is having its opening event on 22nd of January, also at 2 o'clock, and it's in the Bell Auditorium, and there'll be a keynote speech by the director of King's College Digital Lab, so one of the biggest digital humanities labs in Britain, James Smithies, and he's going to talk about the digital modern and digital history. And I think it should be sort of everybody working in the humanities would be interesting to anybody working in digital humanities. So that was what I wanted to say. You can come to talk to me in a break or whatever. Yeah, thank you.
Okay, so I'll leave that information up there unless I need to use the board, which I don't think will be for a while. And we've just had lunch, and now there'll be cake at 2. So we'll see how we go. I'll probably have a break at 1, and then a cake break at 2. But let's dive back into this demonstration and see where we're up to. So what have we done so far? For demonstration 2, writing a script. Here we've defined 2 new objects, and object 1 is an array of 5 items, 1, 2, 3, 4, and 5 to be specific. Object B is an array of 2s, and C is A plus B. And we can run that, and we get C stored in over here as 1 plus 2 equals 3, 2 plus 2 equals 4, and so on. And if we wanted to see C, we just press C, and that's capital C. Okay, so that's where we finished off. Is that okay? Okay, so now what we're going to do is we're going to do the same thing in a slightly different way. And you can think of this part as, so basically we're drawing a line, drawing a path through this conceptual terrain, and it's all very progressive, and every concept builds on the previous concept, and then sometimes we're going to branch off. This is a branch off, so if you don't follow what I do here, that's okay. I'll tell you when we're back on the main line and where everything's super progressive. But I'm going to introduce some more functions that are very useful for making data like this. Because you can imagine if you wanted to have 1,000 ones, that'd be really annoying to have to go 1, 1, 1, 1, 1, 1, 1, 1, 1. Or if you wanted to have, instead of 1 to 5, 1 to 1,000, that'd be really annoying to go 1, 2, 3, 4, 5, 6, and you could make a mistake. And this is something that might actually be something you need to do in your data management process. Like you might get a data frame that hasn't got subject number on it, and you might want subject number on it. You might want to call subject, the first row, subject 1, the second row, subject 2, the third row, subject 3, and you might want to make an array that says, well, an ID number. And that ID number should go from 1 to 1,000 or 1 to, I think, 9 million. They told me that they've got a data set. And 1 to 9 million you're not going to do. So there's a way to automate this sort of thing. So I'm going to show you 2 functions now that I don't want you to stress out too much about and just sort of take at face value. But we're going to make those same variables using these 2 functions. And if you can get the intuition behind that, then that's fine. And it gives you a little bit of more exposure to what a function does and how functions work. So let's clear the workspace with our broom. So now the workspace is clear. And now what we're going to do is do that A variable again. So let's call this manually creating variables. arrays, and then automating. So there's the comments just to keep track of what we're doing. And I put that in the wrong place. Okay, so how can we make this? Imagine that we've got more than 5. Imagine that we've got thousands and we need to make a sequence of numbers from 1 to, say, 1,000. How do we do that? Well, we're going to just do the 5 again. And we're going to use a function called seq, which just means sequence. So what we're going to do is we're going to create a sequence from 1 to 5, where the spaces between the numbers are 1. Okay, so what have you learned here, if you're following through this? It's that you can put in things other than just lists into functions. You can also put in other things that are interpreted by the function to have some sort of meaning. So here, it's not 151 that matters. What we're telling the function is, where does the sequence start? Where does the sequence end? And what's the size of the gaps between each number? So try running that and see what A looks like. And you can see over here in the workspace that A is 1, 2, 3, 4, 5. So it's made a sequence of numbers with a gap of 1 between each one. And it tells us where it starts and where it finishes. And they're the arguments that the function takes. So more generally, what a function does is it doesn't just take numbers, it takes arguments. Sometimes those numbers are arguments. Sometimes those arguments are numbers, and sometimes those arguments get interpreted to do stuff. And that's an important thing to know. Does that make sense?
Yep.
So how do we do this B part? Well, we use another function. We use something called repeat, which is just rep. And here this has only got 2 arguments. The thing you want to put there, and how many times you want to repeat it. So here we want 2 repeated 5 times. And this could be a text item. This could be dog repeated 5 times. That would work fine too. But as it happens, we're looking for a 2. So then we've got a list of 2s. So that's what's saying is the numbers here aren't interpreted as numbers, just raw numbers. They're interpreted as stuff, as arguments into operations or into things that the function has to do to make an output. Yep.
When it's the same number in each column, a 2 here,
Yep.
wouldn't B just be 2 instead of an array?
Here,
Yeah.
it could be, yes, it could be.
Okay.
But we won't, that will confuse things if we talk about that too much.
Okay.
Yeah. Yeah.
So now you have 2 B in your code. Does that confuse?
It will overwrite the old one.
Okay, so the new always overwrites.
Yeah, the newest one always overwrites the oldest one. And here they're just the same thing. Because I put a list of 5 2s and now I've repeated 2 5 times and it's the same thing.
Right, can you repeat the sequence one? That's 1. What's the last one?
The last one is the space between each of the items. So it's saying I want a list of items from 1 to 5 and I want them to increment upwards or increase by 1.
Okay.
So if I were to put 0.5 here, I wouldn't get a list of 5 numbers. I'd get a list of 10 numbers that goes up by 0.5 from 1 to 5. So here you can see we get 1 plus 0.5. We jump up with 0.5. We jump up another 0.5. We jump up another 0.5 until we get to 5. And there's lots and lots and lots and lots and lots of these little efficient things that exist in R to make your life easier. And you don't have to know them all, and I'm not trying to communicate that you should even remember these ones. But the lesson here is that you can, when you're using a function, you're not just taking inputs that are numbers, you're taking things that mean something as arguments for what happens in that function. That's the main message. And then we're going to use this and we're going to play around with this a little bit. So that's our A and our B. So let's, well, another thing we can do, and this is getting a little bit complicated, and it's going to introduce some statistical concepts. So here we're getting our first statistical concepts. And we'll go through this in more detail tomorrow, what we mean by these statistical concepts. But you can also create numbers that, instead of following sort of these rules that we give them, that the function encodes and that we give an input, you can also create numbers as a part of a statistical process. And the statistical process that we're going to use here is a relatively simple process, and that's drawing samples from distributions. Okay? So you'll learn more about the concepts behind this tomorrow. Tomorrow's theory stuff in the morning is all about this sort of stuff. So this is your introduction to the concept of statistical distributions. We'll run through it in practice once now, in this context, and then we'll talk about it in more detail in the theory lecture. So what we're going to do then is we're going to make some new variables. And I'll share my notes with you so that you get all of the sort of good comments and good description. So instead of just writing in lists automatically, or sort of manually, or using simple functions like sequences and repetition to make arrays, we can also use statistical functions. And the simplest possible statistical function that you can use is, or that you can do, is sampling from a uniform distribution. Now, what's a distribution? I'll give you a sort of a very brief introduction to the concept of a distribution. A distribution is basically just the it's the sort of, without getting too platonic, it's the kinds of values, or the rule that tells you the kinds of values that you can get in the world, or the empirical distribution of things that you do get in the world. So if anybody's heard of the normal distribution, right, so the normal distribution is a distribution with a particular shape, and I'm not going to go into the details of this normal distribution, that basically looks like that. And there's certain phenomena in the world that where the frequency or the occurrence of events follows this shape. So if I was to get everybody to line up in their height, I could arrange your height such that putting the tallest person in the middle, you can see this in family photos, right? The two shortest, next shortest, and then so on, we could have you all standing against the wall and making a normal distribution. And that's because height is normally distributed. So it's fordieved, it's divided into the world. The categories that the world's divided up into follow this shape. That's all I mean when I say distribution. We'll go into a lot more detail tomorrow on this. What a uniform distribution is, that there's not really any sort of rules. That any number is possible. So if height was uniformly distributed, people would be different, but there wouldn't be this curve in their differences. So that's the simplest possible distribution that you can get. So let's try sampling a list from a uniform distribution. And let's call it weight 1 for reasons that will become apparent. And the way that we do that is we are running a statistical function now. And something in the environment that will be uniform distributed would be rolls of a dice. Not strictly true, but if I rolled a dice hundreds and hundreds of times, the distributions of you'd get, say if I rolled a dice 6,000 times, I'd have 1,000 ones, 1,000 twos, 1,000 threes, 1,000 fours, 1,000 fives, 1,000 sixes. That'd be nice and uniform. So what we're going to do, yeah?
So weight 1.
Yeah, and this is just a variable that we're creating. So we're going to create a new variable. This is just like A, but we're going to give it a more informative and more useful title. And you'll see why we call it weight 1 in the context of the example. We're going to be looking at weights of different animals to make up. So this is just an array. And we're going to create this array by sampling from a distribution. So this is a statistical function that we're using now. So we're meeting our first set of statistical concepts and our first statistical function. And we're going to do something called random sampling from a distribution. So what the statistical function's doing is it's drawing numbers, basically, from a distribution that looks like the outcome of 1,000 dice rolls. Only the values aren't only 1 to 6, they're from the values that we're going to specify. So that looks like this. This is a function that someone's written. So this is really to get your head around what functions are and what functions do. So this is a function that someone's written. The unif here means uniform distribution, and the R just means randomly sampled from a uniform distribution. And that's a function, so it takes some arguments. And the arguments it takes are, what's the start of the distribution? What's the lowest possible number? For the dice roller to be 1. What's the highest possible number? For the dice roller to be 6. And, sorry? Correct? Incorrect? The arguments this takes is how many numbers do you want? So how many samples are you taking? How many times are you rolling the dice?
30.
So here we're going to put 30. And then what's the lowest possible number? Here we'll put 60. And what's the highest possible number? Here we'll put 120. So that's weight 1. So now we've got an array, and the array is just a kind of variable. It's an object that we can do stuff to. And that is some numbers sampled from the values from 60 to 120, and we've sampled 30 of them. And each value of those numbers between 60 and 120 are equally likely to occur. Is that okay?
No.
Sorry?
I'm just saying no.
Oh.
A desperate waiting. No, it wasn't quite okay.
Okay. Good.
I fell off.
Yes.
No, yeah.
Yeah. But it's a conceptual part that I think
Yeah.
I'm missing. What conceptual part are you missing?
You're doing this with rolls of the dice?
Basically, we've got rolls of the dice, but instead of numbers, we've got an infinitely sided, continuously sided dice.
Yeah.
Or we could get any number between 60 and 120. And each number is equally
Yeah, I
likely.
understand this.
And then we're rolling it 30 times.
Yeah.
And that's all this is doing.
This is what.
That's what this is doing.
Yes.
And that's what it means when it says, take 30 numbers from a uniform distribution randomly. And the uniform distribution is what tells us about the dice. Yeah?
It's not value. It's floating.
They're floating, that's what I mean, infinite. It's an infinitely sided dice. No, it's an infinitely sided dice.
So if you run that again, will the number change?
Yes, it absolutely will. So if you run it again, that's a really great question. So if I run that again, all those numbers will change. Because it's sampling again from that distribution.
So could you then manipulate the data by just keep sampling and go, ooh, I like that one?
If you do that, someone will catch you. There's forensic statistics tools to stop that.
What if you don't know want to have heel intelligence, as it's called in Danish?
We won't get into those details. That's the advanced module. I want people to understand, I want a little exploration of what a distribution is. And a little, tying it up to this idea of what a function is in R. And then that's the level that we're playing at. Yeah? Yeah?
Where does the output
decimal numbers?
Because it's an infinitely sided dice. That's the default. So the default is that we're working just on a continuous number plane, basically, like a number line. So it's saying what it assumes that you want is any number between 60 and 120. And each number is equally likely, including all the decimals.
Okay.
Yeah. So you can constrain that if you want, but then you're using different probability concepts. You'd be using binomial, multinomial type distributions, which is not what we're going to do. Trying to stay away from the mathematical theory. Okay, so that's weight 1. So let's do the same thing for weight 2. And let's have 30 numbers that go from 80 to 140.
Right, so that's you you run the dice for 30 times.
Yep.
And the smallest number is 80.
Yeah.
Okay.
That's it. And going back to assumptions, here we're making as few assumptions as possible about the world. Like we're assuming that there's no priority in any given number. Nothing special about any number. All numbers are equally likely. So basically, if you know nothing about something, you represent that absence of knowledge with a uniform distribution. We're not going to go full Bayesian, but this is sort of giving you the starting points of thinking about Bayesian ways of doing statistics. This is representing ignorance. All you know is the bounds here. You know that the skinniest animal that you're measuring is 60 kilos, and the fattest one is 120 kilos. And that's what the distribution represents. So that's what a distribution represents for us, a probability distribution. Is our knowledge about the relative likelihood of numbers occurring in the world. And if we've got an infinite-sided dice being rolled lots and lots of times, then we could look at the frequency of each occurrence of those numbers and it would have a uniform distribution. So, but that's not sort of the real world. Most of the time data falls into patterns, sort of recognizable patterns, and distributions fall into recognizable patterns. And we'll talk more about this tomorrow. But one pattern that we already talked about was the normal distribution. So heights fall along a normal distribution. And so what this graph represents, this is values, right? And this is probability of those values occurring in the environment, or number of values that occur when I walk around and ask people their heights. And we know that things like height and weight have this kind of distribution, where, say, I'll go for the Australian norm, because it's personally more flattering, of 186 is the, no, Denmark. So this is Denmark, 186 is the norm, 176 is the mean height for males in Australia. So I'm tall. Unfortunately in Denmark it's my height. So most men will be here, and there'll be some that are super tall and some that are short, but there'll be a normal distribution of men. So, can we do that? Can we sample from a normal distribution like that in the same way? So rather than rolling a dice where there's no special numbers on the dice, can we put extra weight on those numbers that are more likely to occur? Yes, we can. And to do that, we sample from a normal distribution. So this is encoding information that we know about the environment. So let's redo the weights again, because we're going to look at weight of pretend animals. And let's, instead of sampling from a uniform distribution, let's sample from a normal distribution. And you don't use these concepts in analysis unless you do Bayesian statistics. You don't use much of this sort of sampling stuff. but it's very useful for checking your data. It's very useful to understand and wrap your head around what a distribution is and what a distribution looks like. So we'll do a little bit of this distributional probability type stuff. So we're going to overwrite our old arrays, and instead of writing R unif, we go R norm, because it's normal distribution. And here we're writing different things. We're not going to write the smallest and the biggest anymore. The smallest and the biggest is only a useful way of characterizing and sort of picturing in your mind a uniform distribution. That's the only facts that you can have about a uniform distribution. What's the smallest number? What's the biggest number? Everything else is equally likely. There's information now in the normal distribution that we can talk about and we can prioritize. There's what we call parameters of a normal distribution. And we'll talk about this tomorrow, so don't worry if you don't understand what that means. And I'll just say it now because there's a whole lecture on it tomorrow. There's two parameters for a normal distribution. One's the average, or the mean, which is the center of the distribution, and the other one is sort of the standard deviation, or the spread of the distribution. So if you can imagine, you've got a population where there's lots of really average people and very, very few tall and short people. You want to be able to characterize that difference as well. Don't worry if you don't have a complete understanding of that at the moment, because tomorrow's lecture's on that. But they're the two parameters that this function needs. So it says, how many numbers do you want? Let's take 30 again. What's the average that you want? Let's take 60 as the average. And what's the standard deviation? Let's take 10.
Standard what? Sorry?
The standard deviation, this fatness of the...
Okay.
And so this is playing again more with functions and statistical functions, and priming you for this concept that we'll talk about tomorrow, which is the standard deviation. But it's okay if that concept goes in one ear and out the other for today. And let's make a vector, or sort of an array of weights 2. Overwrite the old uniform one with something that looks more like what animals would look like, weights of animals would look like in the real environment. Slightly heavier animals on average with the same spread. And then run them. And we'll have a look at plots of that later, but not just yet. We'll just have those numbers there. Those numbers are recorded. Those numbers are in your, now they're weight 1 and weight 2 are in your, those arrays are in your workspace. So R knows they're there and you can access them later and do stuff with them. So let's leave them there for now and come back to it. So another interesting thing we can do is we can make arrays using this repetition and sequence that I told you about before. Not sequence, but the repetition one. We can make an array of text. So if we've got a word that we want to use in our data set, so like if I was to be making a data set, if this was weights of the class, everybody came up and wrote their weight on the board, and then I said which institute you were from, I could efficiently write IKK or IKS using that rep function. Repetition function. So let's do that. Let's say that what we're going to be doing is we're going to be looking at two species of animal, and species 1. So now we're just defining another object. This is another array. And species 1, we want to say every animal in species 1 is, say, a deer. And how many times do we want to repeat that? Any guesses?
20.
30, yeah. Because we've got 30 measurements of weight, or 30 values of the weight. We were doing 5 before, now we're doing 30. So we want 30, we're going to repeat deer, the word deer, 30 times. So imagine all this function is doing is taking your Excel spreadsheet and writing deer 30 times down the row. And species 2, we'll do the same thing, but we'll call it a different species. And I was doing this around Christmas when I was setting this up, so that's a reindeer. And now we've got 30 reindeer. So species 1 is deers, and we've got 30 of them, and they've got weights that are normally distributed with a mean of 60. So your average deer is about 60 kilos. And species 2 are reindeer, and they've got an average weight of about 80 kilos with a bit of variability. And there's 30 of them. So this is the sort of thing you might do with your data set if you're trying to tidy it up. You wouldn't generate your data like this, obviously. Your data would exist, but you'd put labels on it, and you'd want these labeling things to come in. So you'd want to be able to say, oh, okay, so the first 30 subjects I tested were all deer. And you might be out doing field work, recording some information into a spreadsheet, and then you want to add this deer into this sort of categorical label into your data sheet in Excel, and you could go deer, deer, or sort of cut and paste in Excel. But if you want to do it in R, this would be the efficient way to do it. So this can be a useful tool.
But
Yeah.
I'm asking one stupid question.
That's
You know, we made a formula for that.
Yeah.
And this spreadsheet, what is that?
We haven't made the spreadsheet yet.
Ah.
We're putting the spreadsheet together, so it's a fantastic question. Please keep asking these questions. They're very helpful. So yeah, we're putting our spreadsheet together. We're putting it together in bits and pieces. So we've got the labels for all the deers, the labels for all the reindeers and the weights. And if we look at what these look like, we can just sort of type down in the command line like we did before with A and B and stuff. And there's the weights of our deers, and there's the weights of our reindeers. And here's the labels of our deers. Oh, I haven't evaluated them, sorry. So I send that down to the command line, and I send that down to the command line, then they exist. And then there's the deers. Okay, so now we've got these arrays, and they're things, they're objects. Remember I said R is an object-oriented language? Oh. Is there a question that you want to ask? No? Okay. So the next thing is we've got these arrays, and that's stuff. That's just like A, that's just like B. We can manipulate it, we can do stuff with it. And one of the things we can do is take these arrays and add them onto each other. So remember before, when we did this thing called concatenating, forcing to be a list. There we took, say, we defined, what was the specific thing that we did? We defined A, so I'll just write this down in the command line so that you remember. So we defined A as C, 1, 2, 3, 4, 5, right? So we said take 1, 2, 3, 4, 5 and make them a list and call it A. We can concatenate lists. So we can take two lists, say take one list, another list, and make them to be a list. So put them on top of one another. So I'll give you a sort of a very quick worked example here. A is 1, 2, 3, 4, 5. B is 2, 2, 2, 2, 2. So A looks like that. B looks like that. Now what I can do is take those two things and put them together using this concatenate function. So we can have something, let's call it D, where we have A and B. And then D looks like that. Was that too fast?
Just a little bit.
Yeah. So all the C function means is put things in a list. So whatever I put inside of these brackets here goes into a list that I then give a name to. And whatever I put in these brackets here goes into a list that I then give this name to. And this list looks like this, and this list looks like this. What I can do is I can take these lists and put it in the same function. And so all this is doing is it's going, take 1, then put 2, then put 3, then put 4, then put 5. And for the next one it's going, take an empty sort of thing, take 2, then put 2, then put 2, and so on. So what I can do is, I can say take A, and then put B. And what that means is, take all of A, 1, 2, 3, 4, 5, which is a list, and then put all of B, 2, 2, 2, 2, 2. So what that will do, it'll give me all of A, and then put all of B afterwards, and then assign them to an A. Does that make sense?
I forgot, what does that small c stand for?
Concatenate,
Oh,
which is
no.
the STEM word for make it be a list. Will it into being a list. There's Latin everywhere in STEM, it's horrible. Yeah, so that just means listify. So listify, so these things just float around. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, and 5. You're telling R that we're interested in 1, 2, 3, 4, and 5. R doesn't know what you want to do with it yet. But you're telling it listify 1, 2, 3, 4, and 5 in the order that I give it to you. And so similar, A, which is this stable list floating around, and B, which is this other stable list floating around, you're saying, here are these two things R. What I want you to do is listify them. And when I listify them, I put them like this. Is that okay?
What if you write D equals to A plus B?
Sorry?
What if you write D equals to A plus B?
Then it'll do the addition thing that we were doing before.
Okay.
So this is different to the addition. Now we're making the list. We're making a list that has both of our things on it. So that's the function. So functions take variables. This function is make lists. This function isn't adding. If we were to do the adding function, then it would do adding. But now we're telling it make the list. So basically we're really learning how to talk to this R. So now we can do that with our two different animals that we've got going on here. So we can make a weight variable which puts the two weights in a list. And so now that's the outcome of our field observations, is 60 animals with a list of 60 weights. And we can do the same thing with our categorical label that we're using. So now we have an array that tells us what species each animal is. The deers go first, the reindeers come next. And another array that tells us the weight of those species in the same order. Is that okay? What part?
Last one, how to get all the numbers.
How did I get all the numbers? So here, I just did what I was doing before with the A's and the B's, where this one called weight
Yeah,
is just list 1
yeah, yeah.
with list 2 stuck on the end. So we'll do one more thing before we take a break. Yeah. 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 But I'm not going to use that language. It's too complicated. But yeah, that'll be a factor. Yeah. Exactly. Okay, so we've got one last thing that we're going to do. And that is related to your question before. Where is the spreadsheet? Yes. Yeah. Now we're going to make the spreadsheet. So now we're going to make the Excel spreadsheet. And in R, the Excel spreadsheet is called a data frame. So a data frame just means Excel spreadsheet. So what we're going to do is we're going to create a new data frame. So now we're moving up. Do you remember we had that hierarchy of data concepts? We were started at variable, and then we went to array, and now we've been working with variables for a little bit. Now we work with arrays for a little bit. Now we're going to create a data frame, which is the next concept up. And the way you do that is you use a function. And the function, not surprisingly, is called data frame. And so what we're doing is we're creating an object. You can see this sort of logic and the rhythms repeating itself. When we started, we created an object that was a variable, and we could do stuff with the variable. Then we created an object that was an array, and we could do stuff with the array. Now what we're doing is we're creating an object that's a data frame, and we're going to do stuff with the data frame after the break. So let's do that. So let's give our object a name. Call it the deer study, because we're field biologists. And we're going to make a data frame. And that's our function. So this function's kind of related to that C concatenate function, because the C1 says make a list out of this stuff. What this one says is make a data frame out of this stuff. And what you give it is arrays, and what it spits out is a data frame. So you give it some arrays that have got a name, in our case weight and species, and they've got values in those arrays. You give it that and it'll spit out an Excel spreadsheet. So all we have to do is put our stuff in. Okay, so I did something wrong. What did I do wrong? Capital S. It's all, R doesn't know what S with little species with little s is. It's got no idea because I've never told it that. I've only ever told it what S with little s is, not S with big S. So now we've got deer study. And if you look over in your workspace, over here, something new's popped up. Now you've got something called data. This wasn't here before. You've had values before, but you haven't had data before. So now you have data, which is your Excel spreadsheet. So here's your Excel spreadsheet over here.
I got an error.
What is the error say? Species, you've done something similar to me. Have you evaluated these? Have you sent them down to the I do that all the time. I do that so often. Yeah. So now we've got a spreadsheet. We can look at our spreadsheet as if it were a spreadsheet, actually. Although I'm not sure I can remember how to do this. There we go. So up here, it's replaced the script. So your spreadsheet, your Excel spreadsheet exists, and you do that by clicking on the words for deer study. And now you can see the spreadsheet that you made, and it looks like the spreadsheets that you've worked with in other contexts. And that's what R's using when it does stuff. Satisfying. Yeah?
The reason that we have different numbers and weight is just that we ask them to be normal.
They're normally distributed, yeah. We could have gone in and inputted numbers. I mean, I'm very impressed if you're a field biologist who measures like deer weights to 5 decimal places.
Really good one. Yeah.
Or a really bad one who's wasting a lot of time on nothing. Okay. So your spreadsheet's there. And now what we'll do after the break, we'll have a 15-minute break, talk amongst yourselves, look at your code, ask each other questions, ask me questions, and we'll come back in 15 minutes and I'll do some stuff with the data frames. Thank you.